Okay, so having done all that sort of housekeeping, so this is one of my flights of fancy. You may walk out of this and thinking, what's he on about? Why did he bother talking to us about that? Personally, I think I'm interested in, I think if you're a modeler of the world, and that's what we are as GIS people, we model the world, the act of trying to translate the real world into a computer representation of it means that occasionally, well, you have to think about philosophical questions. So one of my examples is if I'm doing a database of, say, urban planning, maintaining the urban environment, in particular maintaining the green assets, there may be a question may arise in what is a tree? Because we want to record the trees to maintain the trees. And we have to ask questions, things like, what is a tree? How do we find a tree? How do we want to define a tree? And then how do other people define trees? Things like that. And these impinge on philosophical questions. Anyway, this is a little slight ragbag of collection of stuff that I've found and find interesting, and think it gives an overarching, trying to give an overarching sort of concept idea as to what we're doing as GIS people with spatial data. So just start with a simple sort of statement. People use geographical information systems to extract data from, that's meant to have an M, data, so that they can make informed decisions. At this point, I shall notice that just tell you that my slides often have the odd typo in. I'm dyslexic officially, so that's my excuse. I can get away with it. But typo errors will sneak in there. Okay, so people use geographical information systems to extract information from data so they can make informed decisions. Does anybody have an objection to that kind of definition? No. Okay. So that begs the question, what is the relationship between data and knowledge? We're saying we're using data to get information, which allows us to gives us the knowledge to make informed decisions. Those are words that we just put down on a piece of paper. What do philosophers think about when they think about, not just philosophers, I hasten to add, think about the relationship between data and knowledge. And this is basically part of the study of the domain, the discipline known as epistemology, which is a sub-branch of philosophy, which is the study of knowledge and justified belief. What is the justification for the things that we do and the knowledge that we create? How can we justify this is knowledge? This is knowledge. So we just have a really brief tour through some of the epistemological ideas that are relevant to GIS. And we'll start with the Enlightenment in the 17th century and slightly earlier, and the two main ideas, philosophical ideas about how we get knowledge, how we get information about the world. And these can be sort of caricatured as rationalism and empiricism. A couple of the sort of flag wavers for the two approaches, René Descartes in regard to rationalism, nationalism, and John Locke regarding empiricism. The rationalism slightly earlier, the workings of the world can be explained without reference to the experience of the senses. We have inherent knowledge and are able to make logical reasoning from within ourselves. Okay, so knowledge comes from within. So, for example, you're born with the innate ability to teach yourself to walk. You don't need parents, other people to teach you to walk. It helps, but you don't need it. You inherently have that ability to walk. logical reasoning. We know that probably the prime example being mathematics. Mathematics comes from number one. We inherently kind of know what a number is, what a unity is, what one is, what two is, and if we put one and one together, we know two exists. So the argument was that we have inherent knowledge and reasoning. I guess René Descartes' most famous statement, "I think, therefore I am," sort of comes to that. Because I can think, that means I exist. We can contrast that with empiricism, championed by Locke and others, that the view comes that the mind is basically born empty. It's a blank, a tabula rasa, and that the knowledge comes from how we experience the world through our senses. So quite different views about where knowledge comes from. Knowledge comes from inside yourself, it's inherent. Knowledge comes from observing the world. Well, not surprisingly, those two views are caricatures, cartoons of the reality of what things are. So this was pointed out by Kant, Immanuel Kant in his famous Critique of Pure Reason, 1871, where he rejected Locke's pure empiricism and saying, by putting forward the argument, the world in itself is unknowable. There is a sort of separation between what's in our heads and the world. We don't directly experience, we can't experience the whole world. The world is unknowable. And that the rational mind, the mind structures and interprets the information that comes from the outside world. So he's basically putting together the empiricism and the rationalism and saying that the observable is structured and conditioned by our internal understanding of how the world operates and our logical deductive reasoning in our mind. Jump forward to the modern time, and this is another way in which these same sort of ideas are expressed, and this is the famous philosopher Karl Popper. Who's heard of Popper? Who's got a science degree? 1, 2, 3, 4, 5, and you've not heard of Karl Popper. Karl Popper is probably the most famous philosopher of science of the 20th century, and he came up with the idea of that knowledge is gained through the falsification of hypotheses. You can never prove things to be right, but you can show things to be wrong. So that's Karl Popper, falsification. And Karl Popper, one of the many things that ideas that came up was with the idea of the three worlds, that we have to think about our experience and knowledge and information in the context of three different and separate worlds. And he identified those worlds as world one, which is reality, what's out there, the real world, so to speak, the physical things, the things that exist in the real world. And he contrasted that, the real world, with our personal knowledge of the world, which is different from the world. There's the world out there, and then there's my understanding in my head of the world out there. But he also crucially identified a third world, world 3, which is called the world of objective virtual knowledge. What that is the artifacts that human beings create that represent and describe and predict the real world. So this is the sort of cultural understanding that we have of the real world. And that is separate from my personal view of the real world. There's my view of the real world, there's the real world out there, and then there's all the documentation, the data, the sum of human knowledge that is put together about the world. And that all these three worlds are separate but interact with each other. So, for example, we observe, as individuals, we observe the world out there. It drives, it enables our consciousness, our understanding of processes in our mind. That causes us to produce artifacts, digital records, papers, descriptions, photographs, any kind of physical or digital representation of that world. And we use those digital representations, both that feed back to our own personal knowledge on the world. We look at the data that's in the computers that we've collected, we read papers, and that recall and consideration of this this objective, this virtual knowledge, restructures our own thinking about how the world operates. And we also use it to describe and predict the real world out there. So he drew up that sort of that diagram, a nice identification of the three worlds, and we can sort of overlay some of the things to do with GIS on top of this and compute. So we substitute these words here. So we have the real world is still the real world. You can't get away from it no matter how you try. If we return world 2 becomes people. And if have you had your introduction to GIS lecture? Is that part of this thing where it says, what is GIS? GIS is made up of people, it's made up of software, it's made up of hardware, it's made up of procedures. Well, and other people. And then we have the software, the databases in which we store our communal knowledge about the world. And we can put I've stuck a few labels on here that we measure the real world. We collate that data into GIS. We experience our worldview and our domain experience is generated through our observation of the real world, but also through our understanding and interrogation of the artifacts that we have in our databases. And we do that through query. We design the databases, our worldview, conditions, what databases we build and how we build them and what functionality we build into them and what we do. So there's a design component. We measure the world and we also predict using various models. We can predict the world and we can make decisions. So we can map on what we do with. So this is a first attempt. This was just done a few days ago. So this is sort of emergent thinking in my own part. But we can map these things that we do in GIS and databases onto Popper's view of the world. About the same time as Popper came up with the idea of the three worlds, Russell Ackoff, he's a systems engineer designer, if I understand correctly. He worked on the design, how do you optimally design manufacturing processes and things like this. That's what he was interested in. That's what his data was. But in 1989, he came up with this he wrote this paper on data to wisdom in the Journal of Applied Systems Analysis, which was an attempt to say, going back to my initial question, is how do we go from data to informed decision making? And he designed or came up with this pyramid, which is called the Data, Information, Knowledge, Wisdom, DIKW pyramid model of the relationship between data, information, knowledge, and wisdom. So we're just going to run through that relatively quickly. So first of all, we need to define what he means by these layers. What are these different layers? So at the bottom, we have the idea of data, and the idea of data is what is a piece of data? Well, the definition that I've got here is that it represents a fact, whatever quite a fact may be. Could spend a day probably debating what facts are, or a statement of event, something happened, something, without any relation to other things. So it's a sort of isolated piece of, I was about to say information, but information is the next level up, so I can't use that. A measurement, so to speak, an observation. So, for example, it is now raining here. It's not, the sun is shining, but that would be, if it was raining, that would be, as long as we knew where now was and here was, and we understood what raining means, that's an item of data, we could say. The temperature is 10 degrees centigrade, the ambient temperature is 10 degrees centigrade. 46 cars passed this building in the last minute. All sorts of things like that you can think of as items of data. It's relatively straightforward. But that's kind of an idealised version of what data is. The reality is that most of us, or many of us, use many other things than a simple atomic items of data, like we've just said it's raining here now. So, for example, this is sort of representing some of my own research, although it's not information to do. It's grabbed from other people's research in similar areas. So, for example, I've worked in the past on the evolution of a group of bush crickets across Europe. And we're interested in how big they are and what their genetics is like and things like that. And how big they are is dependent on the temperature. So we set up an array of data loggers across Pyrenean valleys, up and down the very valleys, and we record the temperature every 15 minutes using these temperature loggers so that we can understand the temperature, build temperature models of these Pyrenean valleys so that we can understand how big the crickets, what are the forces driving the body size of these crickets. So I've got information that is photographs. This is the location. This is my friend here, Nick, pointing up to where this logger is hidden in the bushes. We had a series of photographs of men pointing at bushes. Yeah. We also have a colleague who records the songs of these crickets. So he's got oscillograms or whatever they are. Basically, oscilloscopes, isn't it? It's an oscilloscope, but it's not. But basically, he's got time series of the sound recordings and etc. etc. Here's some 3D scans of beetles in this case. So museum specimens, coats. 3D models that you can then measure precise morphology on them, you know, how long the legs are. We spend a lot of time measuring their genitals, for example. Somebody's got to do it, but it's a tough job. So we've got 3D models, and then once we've got our crickets, we've taken their DNA, we do analyses and we build these evolutionary trees or networks from the DNA analysis of these crickets. And we relate these, I take these evolutionary trees and I spread them across the geographic space and try to understand the evolutionary forces that drive these crickets. The point being here is we're not really interested in evolutionary crickets. The point being is that there's all sorts of different things that we might call data that aren't just these atomic units, items of information or data. So these 3D scans, these oscilloscopes, these photographs, these more complex derived models can always also be regarded as data. Now, this is another example of, or just a version of the pyramid. This one's by Van der Griff, 2008. And you can see here that he's added another layer on here. So he's added a layer called measurement. Now, you might be wondering, well, what's the difference between a measurement and a data? Surely a measurement is where you get data from. Well, that is true, but if you've ever been involved in large-scale data collection undertakings, or even small ones, maybe part of your dissertation in days gone by, there is often what we might call the raw measurements that are made, and then some kind of cleaning, conversion, tidying process goes through, which then results in one's clean data. So for remote sensing, for example, there are the raw figures that come off the satellite sensors, and then there are the products that are created from those raw measurements. So, for example, there may be pixels in the sensor which didn't record data because of a remote sensor, but maybe sunlight scattered into the reflector. Maybe something happened. You get lots of missing data. So the one I do know, for example, is the STRM shuttle topography radar mission, which took radar images of the Earth's surface to build a 90-meter global terrain model, digital elevation model. And how it's done is that you've got the satellite, it takes images, radar images at different angles onto the Earth's surface, and then it uses fancy maths, like ask Mike Smith for the details, to calculate the elevation, basically triangulation to calculate the elevation at any particular point. There are quite a few areas where measurements are missing in this data set because, for example, it's difficult to image and get a decent measurement in a deep valley because you've got to be able to see down it from the right angle. So the measurements may be missing for the deep valleys, but the data set that's issued and published, perhaps they filled those values by getting values from elsewhere or doing some kind of fancy maths on top of the raw measurements. So in this case, Van der Graaf is pointing out that there is a difference between the measurements that are often taken and what is supplied as a data set. Okay, so there is another step here saying that measurements, the data are often not pure measurements, that there is a difference between them. So data is a bit more complicated than just a simple item of data. There are more complicated data types, and there is the problem or the issue of the difference between clean data sets and raw measurements. Moving on to information, back up the hierarchy. Information, I'm defining as embodies the understanding of a relationship of some sort, possibly cause and effect. So in this case, we're taking data and putting it together to find some kind of trend or relationship that exists between items of data. So here, taking an example of raining, an example of information may be the temperature dropped 10 degrees C and then it started raining. So we're connecting a temperature with rain. So we've got potentially some kind of relationship. Well, we've got a recorded relationship between these two. Now, whether there's a causal relationship is, of course, another matter. We'd have to observe many instances of the temperature dropping before rain happening to be able to state that this is a general phenomenon. Nevertheless, this is taking two individual items of data, the temperature and the raining, putting them together to provide more, what in this case is being called information. This has been going on since the beginning of, the mankind, womankind, understanding the nature of the world. So Hipparchus of Nicosia, one of the earliest astronomers, used devices like this to measure the positions of the stars, observe the positions of stars and planets and how they moved in the sky. That data allowed the production of machines like the Antikythera device, excuse my pronunciation. So, Antikythera. And do you know about the Antikythera device?
Yes, I've visited it.
Yeah. It was in the news just last week again, I think. Regularly. Yeah. So those of you who don't know what this is, it was a piece of glass metalwork that was pulled up from a Greek ship and is one of the earliest computation, if probably the earliest computational machine. We don't know who built it. I believe it possibly linked to, I always forget which one is it.
They have, I think, three theories about this, so they're not sure.
Yeah. The basic point is you're taking the measurements taken by Hipparchus of Nicosia and other astronomers, putting those together to create a machine that allows you to which allows prediction of astronomical positions, eclipses, and things like that. So this is taking the data and creating some sort of machine to create and to generate information from that data, or to create a machine from our understanding of the relationships between the data. So, information, putting the items of the data together to tell us kind of stories about the data, we could say. Finally, knowledge. Well, not quite finally, we've got wisdom yet. Knowledge is sort of defined as represents a pattern that connects and generally provides a high level of predictability as to what is described or what will happen next. I couldn't get a nice, concise definition of knowledge. But the basic idea is that you're now putting together the bits of information that you have to provide a more coherent picture of how something operates at a greater scale. So you're taking all these individual observations, connecting them into individual sort of bits of information, and taking all those bits of information and then combining them into a whole so that you can understand how a system as a whole operates. So, for example, if the humidity is very high and the temperature drops suddenly, then the atmosphere may no longer be able to hold the moisture it contains, the solar rays. So that is not describing an individual relationship between individual bodies of information, but it's taken that individual relationships to result in a sort of general theory of how things operate. Here's an example, practical example. So here we're taking information on climate, what we know about climate. Then we combine that with our knowledge about how climate chemistry and physics operates, and that's the basics, provides the basics for climate simulation methods. So we're taking data and knowledge to produce predictions of the world. Here's another, that should be actually on, that was an example, that should have gone with information actually. I was thinking that's just a simple example. A regression analysis is an example of another example of a simple information. You've created, you've got information, in this case on latitude. So this is how temperature changes with latitude. Here's the latitude north of the equator. We get higher temperatures at the equator on average as we go to further latitude. Temperature goes down. We can fit a regression model to those data, which allows us to make predictions. So that was another example of information. The slide just got out of. Finally, oops, oh no. Yeah. Finally. Finally, wisdom, the top of the pyramid. So wisdom is sort of extrapolated. You've got knowledge, you understand how a system works. Now, wisdom is the idea that what do you actually do to the system? Now you know about the system, making decisions as to what you do with the system. So this adds in concepts like right and wrong, good and bad. I understand how the climate operates. I know roughly how it works. In principle, we can seed clouds to create rainfall, which may be highly beneficial in areas of drought, for example. But is that a good idea? It may be beneficial in some ways, but there may be disadvantages in others. So wisdom puts value judgments on top of that. So here's yet another schematic diagram of these things. Rather than this pyramid, it's onto a scatter graph. And basically, we've got two axes here from parts, connecting of parts, formation of a whole, and as they've called it, joining of the whole up there. So as you move through data, information, knowledge to wisdom, you're creating larger and larger sort of structures, views, concepts around your information, from the smallest components to holistic type views of systems, how systems operate. Also, we've got an axis here with understanding. So basic data is sort of involves the researching of a project, collecting of data, then absorbing, doing, interacting, reflecting. Not convinced on some of these classifications, but I agree. One thing that I think is quite interesting is this separation that knowledge, data, information, and knowledge are all about the past. They're all about the experience the experiences that you've had, the data that you've collected. Whereas wisdom is about predicting the future and deciding, making decisions for the future. And there's this separation here that hopefully this component should be relatively value independent, although we've already said from the discussion of World 3 and World 2 that all the data we collect is based on our value judgments as to what is important in the world, so we have to take that into consideration. This is not value free, but it's still hopefully overall less value driven than what we actually do and how we decide to use the information and the wisdom that we create. We'll leave that one, that's just another diagram to say, not a similar diagram. Okay, you've got to watch me turn there. Okay, so one of the things about this, rather beautiful, I like it. I'm a fan of the DIKW hierarchy as a simple conceptual model of the relationship between data, information and knowledge, what we do with data. But it assumes that data is valid, and that is not an assumption we should ever make. We won't leave this course with one thing. I hope it is a deep appreciation that you must be connected to your data, you must understand it before you really know what you can do with it and what you can't do with it, and that this takes effort. A 5-minute scan at a database table and a set of points on a map is not a deep understanding of that data set. So please, when you come across data, then the most important things you can do is to spend time exploring it and understanding it. So here you probably heard the expression garbage in, garbage out. So if we've got garbage data, we may have a perfect model about how the world works, a perfectly predictive model, but if the data that goes into our model is wrong, we're going to get rubbish out. So we have to accept that the data that's being used that you use may be problematic. Okay. This is from a blog spot. I can't remember what the guy's name was, but I thought it was quite a nice little sort of way of exploring this idea about how data, quality of data affects the generation of information, knowledge and wisdom. So what he did was he took the DIKW pyramid and instead of using data, information, wisdom and knowledge, he took the opposites of those. He took words that he thought represented the opposite. So instead of data, incorrect data, falsehood, missing data, information, misinformation, disinformation, guesswork. And then he placed these onto some other pyramids. And he came up with 3 different alternative pyramids. One he called the pyramid of delusion, the pyramid of unawareness, and the pyramid of ignorance. In the first one, you have incorrect data for whatever reason. Maybe you incorrectly calibrated your machine, your data log, which results in misinformation at the level of the information, delusion at the level of knowledge, and, well, they all end up with folly at the end of the day. So basically, through having incorrect information, we've resulted in incorrect decision making. There is also the pyramid of unawareness. There is both data that is wrong, but there's also a lot of missing data out there, so to speak. That's not an oxymoron. I think that's an oxymoron. Personally, one of my interests is the integration of disparate data sets, bringing lots of different information together and trying to connect it together. So in my last job before I came here, I worked on a database of mammals involving range maps, odd traits, things like body size, how many offspring they had, or evolutionary trees, trying to put all this information together to provide an integrated database of learner data. And one of the things that we discovered while doing this, that there is an awful lot of holes and unknowns and missing information across these data sets. So when you bring them together, there's a lot of missing data which makes connections quite difficult to make. But if you've got missing data instead of misinformation, you kind of undertake it. You have to do some sort of guesswork to fill in those missing values. Ignorance follows. Pyramid of ignorance, some data is just plain wrong. So false. So if you've got false data, it is disinformation, it is unawareness. So just bear that in mind, that perfect little model of Ackoff's, the reality is a lot more dirty and a lot messier. Falsehood. That's a question maybe some of you are wondering, well, where does false data? False data is sort of deliberately incorrect data. Why would anybody ever do that? Well, here's a Hobbes cartoon, Calvin and Hobbes cartoon, if you're familiar with them, filling up a reader survey for Chewing magazine. At the end, it just says this magazine should have some using ads. So basically, wrote in a load of rubbish, putting his age of 43, favourite flow book by Governor Curry. He just says, I love messing with data. And people do. My wife, for example, refuses to put in our proper address and our phone number whenever she fills anything online, if she can possibly help it. And people do create incorrect data. So be warned. Some people actually muck with the information. And think of things like Wikipedia pages and things like that. When there's a controversy ongoing, people will hack into the wiki page, change. I'm sure Donald Trump's page is highly locked down at the moment, for example, and probably Hillary Clinton's as well, because people will go on and they will change and deliberately change the information that's available. I also want to show that error doesn't just happen, obviously, at the data layer. It can happen at any of these layers through incorrect reasoning. So, for example, we may have perfect data, but the model we run through it is just not a very good model, so unsurprisingly we end up with garbage results. So it's not just your data you have to worry about, it's the models that you build on. Finally, this is more of the human side of things, is David, this is from a New York Times article by David Brooks. I'm not quite sure who he is. I just found this the other day. And that's so they're asking philosophers, yeah, that's right. They're asking philosophers what some of the most important philosophical ideas when it comes to data and the internet were. And so here, this guy David Brooks identifies this concept, the rising concept of dataism. And I think we've all probably know about this if we've never heard that name before, which is that we will live in a world increasingly where data is available. We also live in a world of quality assurance and tick box checking and everything else to prove what we're doing is worthwhile, show what we're doing, etc., etc. And there is a danger that we come to believe the data more, or let's say we rely on the data and we're measuring everything through the data. And by having this data-centric view of the world, that we understand and we make decisions solely on the basis of hard information, hard data, we're in fact making problems for ourselves. One thing is that there's lots of things that we simply don't have data on yet. So how do those views, those issues get prevalence and get a view in a world in which if you haven't got data to support your argument, people don't listen to you? Okay, so there is a danger that if we emphasise data above all else, that certain aspects of human undertaking and experience won't be included in decision making. And there are other things that perhaps we just can't capture in data. in data very well. Things like people's internal emotional experience of things. We can put numbers to these things, scientists do, but they don't, we know that they don't fully, no number is going to fully capture human experience. So we've got to be wary about this whenever we're dealing with data and people want evidence-based decision-making, that our evidence may be quite biased onto a particular. Right. So, just to conclude, I can see, I thought I was going to run over time, and I think the database models will just have to wait till next week. It won't be a great loss. Everything will carry on. So what did I think? So I thought I'd try and at least put together some sort of tie up this sort of philosophical rambling that I've done about you today into some sort of, I don't know, just what I take from it. So one thing is that we're always learning, and it happens in different ways. So we gain knowledge from observation and both observation and rationalisation. And that in most domains, we need to consider both. Both the data, what the empirical data is telling us, but also we need to consider what our theoretical framework and models are. And how important that is depends on quite often what domain that you work in. So, for example, this is another, you'll see I quite like cartoons and things. We can see that here, this is a cartoon, fields are arranged by purity. Basically, the further over this side you are, the more rational theorising is important in the view of the world. So mathematicians basically don't care about what's happening in the real world most of the time. I'm not saying all the time, but most of the time they live in a world almost entirely pure conceptual theory. As you move to physicists, chemists, biologists, sociologists, psychologists, sociologists, theory becomes less important, or less, we're less able to predict on the basis of theory. More data becomes more and more important as we move towards these, I'm not going to say less pure sciences, but different sciences. So different groups of people put different emphasis on theory and practice. And if you're trying to put experience, when you try and bring together biologists, psychologists, chemists, physicists around a table to talk about a particular subject, often the relative importance of theory versus data is one of the conflicts that these different groups of people may have. So just think theory and practice is important, and data are important in most areas. The other thing is we make the digital world in our own image. We observe and theorise on the basis of your world view. And we must always be aware that your view, my view, is only one view onto reality. Now, that's not to equate all views onto reality in sort of an extreme version of postmodernism. There are lots of different views on the world. They are not all equal, but nevertheless, we have to make sure that our view is one particular view onto it. So, for example, the view, I'm developing a project mapping the water quality and biodiversity of the Hogs Mill River, which is the river that comes down through the campus and out into the river, into the Thames down in Kingston. So there are chemists involved in this project, there are biologists, there are citizen scientists, there are people like the council. We all have different views on this project and what it should deliver, what kind of data should be included, etc., etc. So don't get stuck in your own world. Be prepared to take other people's views on you. Embrace complexity. As we saw with the different types of data, we live in a world where there's lots of different types of information data sources. So when we're talking about managing data in databases, we're not just talking about these atomic measurements, it's 5 degrees C, it rained 25 millimetres of rain. We're also talking about the the databasing of documents, papers, of reports, of video, of images, of spatial data as well. And we have to embrace that complexity. Not everything is simple. We can improve people's lives. Okay, I have another slide, that's more to do with the database section. So what is the point? What does information technology come into it? I haven't actually given you a slide, but I'll just page down really quickly. So this diagram basically takes the data, information, knowledge and wisdom and says, what does information technology do? What does it basically do? Well, what it does is basically allows us to do the heavy lifting on the data that enables human beings to spend their time considering the information and the knowledge generated from the data, rather than worrying about the low-level manipulation of the data itself. Yeah? So information technology, databases, web interfaces, what they do is they free us up from the individual numbers and the individual items of data at the bottom, which means we can interact with it at the information or possibly even the knowledge level, rather than interacting with it at the basic level of the data. And that allows us to be more productive, which hopefully allows us to improve people's lives and how the world operates. And finally, don't be enthralled by the numbers. The numbers are wonderful, I hasten to add. I love the numbers, that's what keeps me in the job and everything like that. But beware. Every number, every data set should have a user beware sticker on the front. Errors in the data and the analytical models we construct can lead to incorrect inferences for decision making. And this dataism problem, that can we measure everything as a number or as a category? And clearly, I think we can't yet. And whether we could eventually or not, I think that's up for grabs. So we'll stop there, because that's quite enough. We'll do the database models next week and the relational, should have time to do that and the relational. Any questions? No. Okay, so in 10 minutes or 15 minutes, we basically meet up in the GIS lab, bring your sticks. We'll just start on load with the first practical, install the OSGS Live onto your data stick, and we'll start just basically learning how to navigate around the environment, the development environment. Okay, how to make a file, copy a file, that kind of stuff. All right.